everyone! This is Jepna from the Discovery Center. In this video, we will describe the effects of solar phenomena on Earth and consider the following big idea. Why do scientists study the sun? We will review how to observe the sun safely, identify some examples of solar phenomena and their impact on the Earth, and finally, use properties of light to make our own pinhole projectors. The sun is our star, nestled in the middle of our solar system, holding this intricate system together and in orbit around it through its gravity. We can feel its influence each day through the heat it provides and the light it shines on our world. The sun also drives our seasons, our climate, our weather patterns, everything that makes the Earth and life on it thrive. From moon phases to solar eclipses, understanding and observing our sun is an extension of understanding ourselves. At 4.6 billion years old, the sun is right in the middle of its life, fusing hydrogen into helium in its core through a process called nuclear fusion. Sustained nuclear fusion is the main characteristic of a star. As a result of the immense heat generated by these nuclear processes, the sun is made of plasma, that is, super hot ionized gas. It is this churning plasma that creates the sun's powerful magnetic field and ultimately drives many of the solar phenomena we observe from Earth, like sunspots, solar flares, and auroras, our southern and northern lights. Sunspots are cooler areas along the surface of the sun with extremely high magnetic fields. In these areas, energy is transferred less effectively from the core to the surface, making them appear as darker spots compared to their surroundings. Sunspots are often associated with active regions on the sun's visible surface and can be origin points of our next solar phenomenon, solar flares. A solar flare is a sudden outburst of energy from these active regions, where tangled ropes of magnetic field lines break through the sun's surface, they snap and reconnect, releasing high-energy charged particles and all forms of electromagnetic radiation out into space, including towards the Earth. When energetic charged particles from the sun collide with gases in the Earth's upper atmosphere, we can observe auroras, appearing to dance in the sky close to the poles of our planet. The charged particles are funneled towards the top and bottom of the Earth by our own magnetic field. The Earth's magnetic field, created by the Earth's molten core, also protects us from the solar wind. Solar wind is made up of highly energetic charged particles, escaping the sun's gravity and streaming out into space. From time to time, the solar wind gets stronger and is able to interact with gases in the Earth's magnetic field, generating those auroras once again. These kinds of solar phenomena are a part of space weather, and like our own Earth weather, have big impacts on our lives. This can be in the form of power outages, satellite malfunctions, and disruptions to GPS and communication systems. By observing and studying the sun, scientists can try to mitigate negative effects on our lives on Earth, and even for astronauts in the International Space Station. Understanding and forecasting space weather will also help inform future space exploration as crewed missions look to explore other worlds. So, what are some methods of observing the sun safely? Never look at the sun with the unaided eye. There are many different ways to study and observe the sun, from solar telescopes to eclipse glasses to sunspotters. Today, our mission is to make our own pinhole projectors, a simple way to view our sun safely. You may have heard them called pinhole cameras, though there's no film used, or camera obscuras. In a typical projection or camera setup, an image is created by focusing light with the use of lenses. With a pinhole projector, there are no physical lenses. Rather, a small pinhole acts like a tiny lens. Light enters the pinhole, it gets focused, and then is projected out of the other side. When the projected light reaches the surface, you can see an inverted version of the image that passed through the pinhole on that surface. Here, gaps in a colander act like pinhole projectors, showing tiny images of a partially eclipsed sun on a table. Here are some materials that I will be using for my own pinhole projector to view the sun. In designing your own projector, consider what material will act as your screen, where the pinhole should be placed, and how you will angle your projector for the best viewing. Experiment with different build setups and materials and see what works best for your observations. You may need to build various iterations of your own projector to achieve the best results for your purposes, so think about what factors in the design of a pinhole projector will impact the image of the sun. How does the size of the pinhole affect the resolution of the image? What about the distance of the screen from the pinhole? Here is my first prototype of a simple pinhole projection setup using a cereal box, aluminum foil, tape, and a white sheet for a screen. Angling the projector such that sunlight passes through the pinhole, here we can see a small image of the sun, and I could make out the clouds surrounding it as well. If I want to observe a larger image of the sun or more details on the solar surface, I may need to adapt this design and try again. How can you use this type of projector to safely view a solar eclipse? Can you see any sunspots? How can you adapt or modify your design to view sunspots? What do you notice about the position of any visible sunspots over the course of multiple viewing days? What about a month? What conclusions about the physical mechanics of the sun can you draw from observing sunspots?